then f sub minus n will be equal to magnitude of f sub n e to the j theta of minus n, right? What do you know about if this property is true? Theta of minus n, how is it related to theta of plus n? How are the two phases related? If I put theta of n here, just a negative sign, right? Just a negative sign. If this property is true, okay, if this is the complex conjugation of that one, okay, theta of minus n must be negative theta of n if this property is true. Okay, so the two phases are related in this manner, and that allows you for a way of writing this into a compact form, because then you can write this as being equal to, okay, take out the DC term. You can take out the DC term and write the F0 term up front, okay? And then you can write the leftover term, n equal to 1 to infinity, just like what we had before, okay? Just like what we had before, except that the first term can be written as magnitude of f sub n e to the j n omega naught t plus j theta of n. Okay, the first term will just become like this because I just write my f sub n in this manner and put the phase into the exponent. Okay, that is the first term. What happens to the second term? Second term would have this thing over here, but this one, I can write this as f of n magnitude, just like what I have done over here, e to the minus j theta n. Agree? This term just becomes that, because I proved that this thing is a negative of that thing. So the second term will look something like f sub n e to the minus j n omega naught t, and then with the minus j theta n here. Okay? And now you can see that you can compress the two together using some cosine identity, or using some Euler's identity, or whatever you have learned in trigonometry. So how do the two terms compress to one? Yes, Devasia?
Sorry,
What is that? You forgot my question?
yeah, so compressing the terms. I guess you could expand about it and compress them, but yeah, I'm not sure.
Okay. Pokari, you remember?
You can take out a negative for the exponent,
Yes.
and then that's 1 over the exponential term,
Okay.
and then you could multiply
Okay.
the first term. And
Okay. Not quite Titus. What do you think?
I'm not sure. Can you just add that there?
Well, you can actually factor out the f sub n, right? You factor out the f sub n, and then what you have is e to the j n omega naught t plus theta n for the first term. The second term would be just equal to e to the minus j n omega naught t plus theta n. Okay, what does that give you?
there's all like cosine.
Is it 2 cosine? I mean,
It's a 2 cosine, right? It becomes a 2 cosine. That two terms add up to give you the 2 cosine. Okay? So finally, the compact form has this final form. Okay, if f of t is real, it has this final form that looks something like this. F sub 0 plus n is to the 1 to infinity 2 times f sub n magnitude cosine of n omega naught t plus theta sub n. This is called a compact form. If f of t is real. And can you see that the sum is always real value? Every term in this series is real value. Okay, so it always adds up to the real number. Okay. So are there any questions regarding this Fourier series expansion? Okay.
Get the function.
So I have about 10 minutes left. Maybe I can teach you how to find these coefficients. If you know this function, how do you find this coefficient? Okay. Are there any questions regarding these different forms? But the exponential form is the most convenient one. Most convenient one in my opinion. Okay? So, in order to find these coefficients, let's talk about the concept of orthogonality. Okay? And all of you know about vectors, right? You have learned about vectors. Have you learned about vectors? Maybe in Physics 212 or EC 110? Where else did you learn about vectors?
Linear algebra.
Math, linear algebra? Okay, good. So if I have a vector, three vectors, say AX, AY, AZ, I can always write it in terms of AX times 1, 0, 0 plus AY times 0, 1, 0 plus AZ times 0, 0, 1, right? I can always write this, and I can call this unit vectors, okay? U1, U2, U3, okay? Hence, I can have any vector of A, this denotes a vector A, it can always be expanded in terms of unit vectors, U1 plus AX, U2 plus AY, sorry, plus AZ, U3. This is quite clear, right? Any vector A can be expanded as such. And what do you notice about the unit vectors? They are what? They have length 1. What else do you notice about them? They are orthogonal. Okay? They are orthogonal to each other. That means that U1 dot U2 is equal to 0. Okay? In general, Ui, maybe I put a transpose there, just to follow linear algebra notation. Ui transpose dot Uj is equal to delta Ij. This is called the Kronecker delta function. Kronecker delta function. The Kronecker delta function has a property that it is equal to 1 when I equals j is equal to 0 otherwise. Okay, it has this property. So you can denote orthogonality in this manner, but these unit vectors are more than orthogonal. What do you call them? They are
Orthonormal.
orthonormal. Okay, they have length of unit 1, so that if you pick any one of them, okay, and dot with itself, it always gives you 1. This is the property of orthonormality.
Wouldn't they form an orthonormal basis?
What is that?
Wouldn't they form an orthonormal basis?
Yes, they also form an orthonormal basis. Okay, they form an orthonormal basis. But if you need to find the coefficient, AX, AY, AZ, how would you find that? It's very similar to the Fourier series expansion. With about to find this coefficient f sub n. Okay, but this is just a very simplified form of Fourier series expansion, the simplest that you can ever think of. And if you're given the left-hand side, how do you find ax, ay, and az? Okay, what do I do to find ax, ay, and az? Rawat, what do you think?
I have no idea.
假设是加好啊 I forgot the name. 假设
I don't know.
No?
I don't know.
You don't know? Okay, you don't know the answer or you don't know your name. Liu Chunzhang? Yeah, Liu Chunzhang, right?
Yeah.
Okay, how do you find ax, ay, and az? No, no idea. Okay. What about Emmanuel? Set to 0? No. We use the orthonormality property of the u's, right? So if I were to multiply this equation, say by u1 transpose, and dot multiply by that unit vector from the left, what do I get left? In the equation on the left-hand side, I have u1 t dot a, and what do I get left on the right-hand side? Ax, very good. Okay, so a simple way to find ax is just using the orthonormality property of these functions, and then I can do the same thing for ay. I can do the same thing for az. Okay. So if you find some orthonormality, that's a very difficult word to pronounce, orthonormality property of this function, okay, you can use the same kind of trick to find this. Okay, and how do we find the orthonormality property of this function? Well, this concept can be generalized to not only three vectors, these are called three vectors. Okay, you can generalize it to a vector of any length. A might be a1, a2, an, and it can always be expanded in terms of a1, 1, 0, 0, 0, 0, and so on, 0, plus a2, 0, 1, blah, 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 a3, blah, 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 all the unit vectors, right, 2, plus an, with 1 at the end, right? You can always expand any vectors as such. And you can say that any vector A can be expanded in terms of sum of AI, ui, and if you call each of these ui, I equals to 1 to n. And how do I find ui? Right? How do I find ui? Anybody? What do I dot this equation with? Yes, Dabasia, what do you think?
I guess that UI is always 1, right? Since it's
No, ui is any of this vector. This is u1, u2, and this is u3 perhaps. And this is my last unit vector, u sub n. Right? And then, given that all these vectors are orthonormal, how do I find my a sub I in general? I use the same trick as I did here. I dot it with I pick a u and dot it with that u. I pick a u, very good, okay. I pick a u and maybe I call it a different u from this one. The index over here. And then if I do that, then what happens to this summation over here? Everything would be 0, right? I have this this property. I have this property that they are orthonormal. Okay? And everything of this inside this summation would dot to 0, except for one term. Which term would remain on the right-hand side? The j term. Okay? uj dot uj. And this is equal to 1. So I have aj. So given the very complicated expansion vectors, you can still find the coefficients if you can make all the functions orthonormal. So if I can make this function orthonormal, I can find these coefficients very easily. And next lecture, I will prove that these functions can be made orthonormal, just like those unique vectors over there. Then there will be a very simple procedure to find this coefficient until you stop